Alright guys, today we're going over inscribed angles, section 12.3. Again, we'll be learning some new theorems, so if you've already had a place where you've written down most of your theorems, find that to continue writing those. So right now we'll go over the inscribed angle theorem. First, let's describe what an inscribed angle is. An inscribed angle is an angle where the vertex is on the circle. Okay? So remember, circular angles that we've been talking about start at the center and reach out to an arc, but an inscribed angle starts on the circle. So again, our central angles that we've been dealing with start at the center, but an inscribed angle starts, its vertex is on the outside of the circle. So the inscribed angle theorem states that the measure of an inscribed angle, so this angle ACB here, is half the measure of its intercepted arc, AB. Right? So here's the equation. The measure of ACB is equal to half the measure of this angle. Right? Where again, this angle that we attribute with this intercepted arc is actually the angle that you get from a central angle, right? So if this central angle is 40, we would then say that the arc also measures 40, right? So these two are pretty much directly related. Now what we're saying is this inscribed angle theorem, what we're saying through this is that this angle right here is half of this measure right here, therefore making it 20 degrees. On the illustration, you should see that this angle is definitely narrower than our initial angle. So that's what we mean by it's half the measure of the intercepted arc. So very quickly to reiterate our last point, if we have here an inscribed angle ABC and its arc is 100 degrees, what would the measure of this angle be? So again, we've learned the equation will be that the measure of that angle is going to be equal to half of the arc, which the arc is measuring at 100 degrees. Again, just to reiterate, we define this is 100 degrees because the central angle to create this arc is 100 degrees, right? It's not just an arbitrary number. That's how we define the measure of the angle, but you guys already know that. So again, so that would mean that x is going to be equal to 50 degrees. All right, moving on. Question 1. So here we have the measure of ABC is 32 degrees. So I would like to know what the measure of arc AC is. I'll now pause for 2 seconds. And now we will move directly into question 2. This is using the exact same idea, but a little bit more difficult. Here we have an inscribed angle ABC measuring 71 degrees, and I would like to know what the value of x is below. All the information you need is right here. You may want to pause it, so I'll give you a couple seconds. All right, guys, so we're moving pretty quickly through this section. It's not too difficult. So we're going to continue with that trend and kind of talk about the remaining three theorems very quickly. Okay? Now, these theorems are not something that you necessarily need to memorize because they can all be derived from our earlier theorem. However, it will make your life a lot easier if you recognize these situations and can apply them without having to dig deeper. Let me show you what I mean. So here's our first theorem, okay? And it states that two inscribed angles that intercept the same arc are congruent. So here we have angle NPJ, and it has an arc right here. And we have another inscribed angle NYJ intersecting the same arc, right? So just common sense wise, it would make sense that if this angle, so let's say that JN is 80, right? A little thick. Then NPJ would be half that length, or 40 degrees. Now again, if you just applied our first theorem, if NJ is 80, then we would know that angle NYJ is also half of 80, or 40 degrees. So again, you don't have to memorize this, and it does seem to make common sense, but something to remember. Now this one's a little bit trickier to see sometimes. Some of the problems we'll be dealing with will have a lot more complex lines within the circle, maybe something that looks like this. But the key idea here is that if you have an inscribed angle that outlines half of the circle, you know it's going to be a right angle. Now that should make sense for reasons we already know. We know that if you take the measure of all the arcs on the outside, they add up to 360 degrees, right? The angles that we can make from the center, no matter how many different types of angles you can create, they all add up to 130 degrees all the way around, right? We've even learned that when we were finding the area of polygons, right? So if we know that this is a semicircle, that means that this arc right here has to account for half of the total amount of degrees, right? Half the circle has to account for half the degrees. So if we divide that by 2, promise you that's a 2, then we have this semicircle taking up 180 degrees, right? So if this semicircle is taking up 180 degrees, then that means that angle JPN must take up half of those, or a clean 90 degrees, or as we said in the theorem, a right angle. Okay? So again, these aren't things that you can solve all the problems we'll be doing without these theorems, but this is harder, this theorem right here is harder to intuitively reason out on your own unless you've at least seen it and in the back of your mind somewhere are looking for this type of situation, right? Okay, and this last theorem is actually built off of this one. It says that in the opposite angles of a quadrilateral inscribed in a circular are supplementary. Okay, interesting. I'm sorry, it's not built off this one, but it's a similar idea. So here we have angle, let's take these opposite angles, angle N and angle A. Okay, so let's first look at angle J and P. So the way that these quadrilaterals are kind of the way that they're defined is that we have 4 sides. Now the reason that this theorem works is because these angles, angle N and angle A, these opposite angles, meet where they intersect the circle, right? So let's look at the arc that angle N creates. Okay? So angle N is now creates this arc right here. So this is what angle N is responsible for. Now let's look for what arc angle A intercepts. Angle A intercepts this arc right here. Now if you see these two angles together account for the entire circle, right? So that means that the arc created by N and the arc intercepted by A add up to 360 degrees, right? So that means if both of them added together, so if arc N, so the arc, this is not the correct notation, but there's not a lot of room here. So we'll just say the arc created by N plus the arc created by A equals 360, right? Then that means that the measure of each of these angles, right, the measure of N plus the measure of A must be equal to, as we learned earlier, right, the length of the arc divided by 2. which comes out to 180 degrees, which means this angle N plus this angle A equals 180 degrees, or are supplementary to each other. Again, you could do this for angle P and angle J, and you would get the same thing, right? Very quickly. Angle P right here inscribes this angle over here, and angle J inscribes this angle over here. Again, the two angles added to the two arcs added together adds up to 360 degrees. So applying the first theorem that we learned, you should be able to say that angle J plus angle P equals 180 degrees. All right. Moving on to our last theorem. Our last theorem states that what we have in this case is a very specific example. What this theorem, which in your book is 1212, states is that the measure of an angle formed by a tangent, here we have tangent A, and a chord AB, is half the measure of the intercepted arc. So here this angle caused by the chord and the tangent, this angle 1, this angle right here is half the length of the arc that is made up by this angle, right? Or I'm sorry, exists in this angle. It's not defined by this angle, right? And we have the same thing on the other side, right? We have another angle formed by the tangent intercepting the chord, and that is this blue angle, right? Arc BCA is within angle 2. So again, we would say that angle 2 is equal to half the measure of BCA. Okay? Again, you'll only see this in very specific circumstances, so you definitely need to remember this equation, as we'll see going into the next question, which is slightly more difficult. So really make sure you understand how this works. All right? That this chord intercepts with this tangent and creates two different angles, each angle measuring half the measure of the arc consisted inside of that angle. So here we have question 3. Question 3 is asking, what is the measure of arc X? So here we have arc X, and here we have another arc, and angle 50. Now there's two ways to solve this. You could first continue drawing out this tangent and deriving some other information based off that, or finding the measure of this arc and then using that information to help you find the value of X. Either way will work. Hopefully those suggestions helped, and I will now pause to let you answer it.